Hello students, I hope you're having a wonderful day. Today I would like to complete a practice problem from chapter 6 with you. It's over projectile motion. So what I'm going to do is read the problem to you. We're going to write down some knowns and unknowns, and we're going to draw a picture and then solve the problem. So let's go ahead and get started. A soccer ball is kicked at 21 meters per second at an angle of 40 degrees with respect to the horizontal. Now in this problem, it wants us to calculate the maximum height of the ball. This is known as y max. So I'll just write that in here. So we have y with a subscript of max, and then in part B, it wants us to calculate the displacement in the x direction. And this is known as range, identified by capital R. So let's go ahead and draw a simple picture. So we have the person kicking the soccer ball at 40 degrees. Okay, and I will identify y max right here. This is y max, and the total displacement in the x direction is known as range. So our range is right here. Now what we're going to need to do is break this initial velocity vector down into its x and y components. And the initial velocity of the soccer ball is 21 meters per second. So let's go ahead and calculate the x and y component for that velocity. So the velocity in the x direction is calculated by initial velocity times cosine of the angle theta. Well, initial velocity is 21 meters per second times cosine of 40 degrees. So go ahead and get your calculator out. 21 cosine 40 is equal to 16.08 meters per second. Now we need to calculate the velocity in the y direction. This is initial velocity times sine of the angle theta. So initial velocity, 21 meters per second, times sine of 40. And since our value is our angle measure is less than 40 degrees, we can make the prediction that the y component of velocity will be less than the x component. So 21 times sine of 40, we have 13.5. And we are in units of meters per second. Okay? Now, one thing that's important when we start calculating things in the y direction, we need to know that the acceleration in the y direction is the acceleration due to gravity. So I'm going to write that down here. Acceleration due to gravity is identified by lowercase g, and this is negative 9.8 meters per second squared. Now, before we calculate the maximum height of the ball, we need to calculate the time to reach the maximum height. So, what we're going to do is say that the acceleration of the object is equal to the change of velocity in the object divided by the time interval. Now we're going to take this base equation and adapt it to our situation for projectile motion. And so what we're going to have here is the acceleration in the y direction. We've already identified that it's the acceleration due to gravity. So this is g is equal to the final velocity in the y direction minus the initial velocity in the y direction divided by the time to maximum height. Okay? Now, what we're going to do is isolate delta t sub max. So we're going to multiply delta t max on both sides of the equal sign and then divide by the acceleration due to gravity. So what we have is delta t sub max is equal to v sub f sub y minus v sub I sub y divided by the acceleration due to gravity. Now, the final velocity in the y direction. Now we're talking about the time to achieve y max. Well, the velocity in the y direction at maximum height is equal to 0. So velocity y sub max is equal to 0 meters per second. Okay? So if this is equal to 0, let's just get rid of this guy. Okay? Now it's important that we do not get rid of our minus sign here. So algebraically we are required to keep the minus sign there. So we have a negative initial velocity in the y direction. Now you guys have already calculated this. The velocity in the y direction is 13.5 meters per second. But we have to keep the negative. So negative 13.5 meters per second. And we're dividing this by a negative 9.8 meters per second squared. So we have a negative in the numerator and a negative in the denominator, so we know that we're going to have a positive value because the negatives will cancel each other out. So 13.5 divided by 9.8, I get 1.377. And let's take a look at the units here. In my numerator, I have units of meters per second, but in my denominator, I have units of meters per second squared. So when we divide those, remember the old algebra rule that tells us whenever we divide fractions, it's like multiplying by the inverse of the denominator. So this is going to give me meters per second times second squared over meter. So our meters will cancel. A second cancels, and one of our seconds up here cancels, and we're left with units of seconds. Now I'm going to put a dotted box around this guy because we're going to need to use that in the next step when we calculate y max. So we're going to start off with the base equation to calculate the maximum height of the soccer ball. This is final displacement is equal to initial displacement plus initial velocity times the time interval plus 1/2 times acceleration times delta t squared. Now, we're going to adapt this equation to our situation, and we know that the final displacement in the y direction, what we're looking at is y max. So y max is equal to the initial displacement in the y direction, so d sub I sub y, plus the initial velocity in the y direction, which you've already calculated that right here at 13.5. But I'm going to finish writing the equation and then we will plug in our values. So multiplied by delta t plus 1/2 times the acceleration in the y direction, and this is going to be acceleration due to gravity, times delta t squared. Now, what I want to point out here is this time is the time to maximum height. And you guys have already calculated this at 1.377 seconds. So what let's do is put a subscript to help identify this variable of time. Let's add max. Okay, because we're looking at delta t max. Now, it's very interesting here, the initial displacement in the y direction. We're looking at our picture, it's 0. So y max is equal to initial velocity in the y direction is 13.5 meters per second times the time interval to the maximum height, 1.377 seconds, plus 1/2 times negative 9.8 meters per second squared, multiplied by delta t max squared, so 1.377 seconds squared. Okay, so what let's do, go ahead and get out your calculator. Let's take the product of these two values here. So initial velocity in the y direction and the time to maximum height. So I have 13.5 meters per second times 1.377 seconds. This gives me 18.59. Let's take a look at the units. I have meters per second times seconds, and algebraically we can write this seconds as seconds over 1. So I have a unit of seconds in my numerator and units of seconds in my denominator here, so those can cancel, and this leaves me with units of meters. So we have 18.59 meters plus 1/2 times negative 9.8 meters per second squared. Now the reason I'm writing it like this is because if we're looking at the last part of this equation here, according to the order of operations, you know that we are required to take care of our exponent first. So what we're going to do is 1.377 seconds squared. And not only are we squaring the numerical value, we are also squaring the unit value. So seconds times seconds, we're going to have units of seconds squared. So 1.377 squared gives us 1.896 seconds squared. Okay? So I'm just going to rewrite this 18.59, and we have plus, so 1/2 times negative 9.8, we have negative 4.9. So that times 1.896 is going to give us a negative 9.29. And we're going to have units of meters. Right here we have meters per second squared times second squared, and we can write that as second squared over 1. Our units of second squared will cancel. So right there. So 18.59 minus the 9.29 meters, this gives me 9.29. So Y max is equal to 9.29 meters. Okay, so let's go ahead and write that up here. And what I'm going to do is I'm going to erase this to free up some whiteboard here. Okay. Now, the problem wants us to calculate the displacement in the x direction, which is known as the range, identified by capital R in part B. Okay? Now, the equation that we're going to use is range is equal to the velocity in the x direction multiplied by the total time that the projectile is in the air. Now, the problem here is we do not have the total time. We had delta t max, which I believe was 1.377 seconds. Now, to calculate delta t total, this is 2 times delta t max. So 2 times 1.377 seconds. This gives me 2.754. So delta t total 2.754 seconds. Okay? Now, we have already calculated the velocity in the x direction when we performed vector resolution earlier in the problem. So right here, remember when we performed vector resolution, our initial velocity, so the person kicked it in the air at 21 meters per second, we calculated the x component of velocity at 16.08 meters per second. So range is equal to 16.08 meters per second times delta t total. And remember, this is 2 times delta t max. So we have 2.754 seconds. And our units of seconds is going to cancel out. So 2.754 times 16.08 gives me 44.28 meters. So for part B, the range is 44.28 meters. And this is the answer to part B. So I hope this video has helped you with this practice problem. If you have any questions, please give me a call or send me an email. I hope you have a wonderful day.